Welcome back. So in this video, we're going to discuss section 16.6, which is titled Parametric Surfaces and Their Areas. We've already done parameterizations, polar coordinates, spherical coordinates, and the like. And for a circle, for example, you considered a function that when you varied theta, gave you values of x and y. So for example, you had some function on the unit circle, right? It took theta and it produced cosine theta and sine theta. Now I wrote that as I wrote that as a vector. So I wrote this as a vector in two-dimensional space. So we went from the theta, which is varying from 0 to 2 pi, and so this is going to go from a line to a circle, right? And the function that connects them, I'm calling f. Okay, so this is a type of parameterization where if you give me a theta, I'll give you a spot on the circle. Now, we are assuming that the radius is fixed, and obviously if I vary the radius, I could come up with something more complicated. Perhaps it spirals out, right? But if that's the case, then I have to add a factor of r, for example, so that at the origin, right, maybe it's equal to 0. In any case, we have these. We have this general formula which takes a pair UV and produces a vector in the three-dimensional world. So it's going to consist of x, y, and z coordinates, and each of those is a function of u and v. So you go from this two-dimensional thing to this three-dimensional blob. If I give you a point u0, v0, this is going to give me some point in the blob. And though this is a two-dimensional thing, and this is three-dimensional, this really should not surprise you that you can get more dimension out of something with fewer dimensions, becoming a two-dimensional thing becoming a three-dimensional thing. Because, for example, when I had theta, what I wrote previously, I gave you a circle. Well, technically a circle is one-dimensional, but you draw it in a two-dimensional area, just like this blob is embedded in a three-dimensional world. So that's basically what we're doing. So let's give some examples, some more examples that look more like this. So here's one from your textbook. We want to find the parameterization of the sphere okay, so I'm just asking, can you find the parameterization of the sphere? So this is not difficult. Let us recall that if the sphere has radius a, well, if I give you the spherical coordinate system, this should help. So in general, the spherical coordinates say that rho of sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. Okay, so that is the general spherical coordinate system. Now, this is a sphere, right? A sphere of radius a, and rho is the distance from the origin. Well, you're always a distance a away on a sphere of radius a. So I'm just going to replace all those rhos with a. Okay, so is this not exactly what we wanted? Is this not the parameterization? It is. So to sort of make it official, I will rewrite it in this form. So instead of u and v, we're going to have phi and theta, and then I'll just replace x, y, and z as appropriate. So this will be a sine phi cosine theta, right? A sine phi sine theta, and then for the final coordinate, a cosine phi. Okay, so this is just one example of a parameterization. Your book gives several more examples, and they're frankly not all that interesting. So I advise you to do them anyway. Read through the book on those examples, but they're not very deep. I guess if you have any questions, we can have a chat about it. But in the next video, I will discuss how to compute the tangent plane to a surface.